Hello everyone, I'm Jun Sun. I'm going to present you a paper. Are we pruning the correct channels in image-to-image translation models from Beagle, Tohoku University, and Nikkei Epicenter. And first, I will give you a short answer to the title. That is no. So, generally, when we want to prune some neural networks, we use a lot of regularization on the channels. So, for each kernels, we multiply it with some lambda, then we regularize the lambda, and we choose some thresholds and prune the network that is learned with a small lambda. So, this is good, but it is not always correct in our case. So the background of our study is the image-to-image translation model is still the most popular employed on the edge device and mobile applications, just for some cool visual effects. Therefore, just to obtain compact models with pruning distillations are very common in practice. And we focus on architectures with stacked convolution, instance norm, and ReLU layers. So this type of modules are edge device friendly. So actually deploy such architectures on the mobile phones. So one commonly asked questions, so why we cannot use this general purpose pruning method? Because the visual effects are more sensitive than other tasks, such as classifications. A small perturbation in the input will cause totally different outcomes. So next, we begin with the analysis of the perturbations. So first, we define a sensitivity measurement of the output with regard to some input. So the important part is the variables gamma and beta in the instance norm. So the gamma is the rescalar parameters and the beta is the Bayes terms. These are both learned during the training of instance norm. So with this sensitivity measurement, we can calculate it how if we prune some channels, then how much the perturbation shape will cause. The perturbation here is defined as our norm of the difference of the outcomes. So here we have three conditions. So the first condition, when beta is larger than the normalized gamma value, then that means the beta is not important in this scenario, so we can simplify them. So here is some example of error bound. So we have our official released circle gun models, and we select some channels to calculate their error bounds, and then we prune them, we remove them and see how the actual outcomes changes. So it can be seen that if we remove the kernels with larger error bound, then the outcome will change significantly than this with smaller error bounds. So next, we will talk about how we actually use this error bound as in the pruning. So here the major idea is to use it at loss, and minimize this loss will make some of these channels to have larger error bounds than the others. Therefore, we can just choose these ones with smaller error bounds and to prune them safely. And this is defined as the follows. And in the equation 4, so we have our loss as the perturbation error bound of all the channels of all the layers. So next, we update the rescaler parameters of the instance norm. We set it to 0 if one of the 4 following conditions is satisfied. So the first condition is the instance norm will output a negative values, so which will be 0 after reload, so it can be pruned. So next one is it is initially just have 0 gamma values, so it will always output the beta no matter whatever input is, so it can be pruned. So the third one and the first one is if and in the denominators is the perturbation error loss of all the channels, and above it is the perturbation error bound of a certain channels. So here we calculated how much a channel contributes to the total perturbation error bound. So we choose some threshold, rho 1, rho 2, for the one with beta without, and so we choose a small threshold. So if the contribution of channel is small to the total error bound, then we say it is probably more safe to prune it. And we increase the threshold after the numbers of several channels stops decreasing during tuning. So we will just make it larger. We will make more channels to be pruned by changing the threshold. So next, we're going to show you how our method actually works in the experiments. So the first one is the multi-stage training and the comparison of the stabilities. So our method is denoted as the BIGP, and the reference model is the gunslimming GS32, which uses the aforementioned lasso regularizations as the pruning algorithm. So the figure in the left shows how the numbers of channels and the FID score changes along with the training progress. So it can be seen that if we use the lasso regularization, then the numbers of channels will decrease very fast in the early epochs. And as a result, the FID score, which indicates the quality of the output, will go bad. And on the other hand, we use multi-stage, thresholds in our method, and we stably we just reduce the channels stably, and we finally reach some better performance than the reference model. So next we'll show you the actual qualitatively results of our methods compared to the reference model. So one interesting observation is, as you can see, the strips of the Zember. So the output of our method just have similar visual looks of the original model, but instead the reference model, GS32 model, just have totally different output. The strips compared to the original model. So this further confirms the stability of our pruning approach. And of course, we achieved better flops and memories and FID scores. And in the last, I will show you how our method works with distillation models. Here we choose the currently best performing distillation models, that is OMGD. We download their official released weight parameters and use our perturbation error bound to show if show if there is still room to prune this model further. And here in ZSP, which stands for the zero-shot prunings, so we choose two of these channels with the least perturbation error bound, and we prune that we can see that it doesn't change the visual effect at all. And next, we combining our purpose and loss term during the training. Then we can further push the performance. We have 10 channels print with lower affinity scores. And thank you very much. More results can be seen in our supplementary materials. Thank you.